Talk BC, 410 office hours. A little multiple choice for response practice. Okay. The answers, if you want to check them real quick. Multiple choice. Number 1 is A. Number 2 is E. Number 3 is B. Number 4 is D. 5 is C. 6 is E. 7 is A. 8 is B. 9 is E. And 10 is D. All right, that's just the multiple choices. Okay, so first one, the Cartesian equation of polar curve. Okay, so if we were to do a quick sketch of this, that would probably help. 1, 0, 1. And that's what the graph looks like. It's centered at 1/2 comma 0, and it has a radius of 1/2. So, of these equations, which one? I mean, we could just try and write it like we're going to write it anyways. These is all kind of weird. So it'd be x minus 1/2 squared plus y squared equals 1/2 squared. So if we were to FOIL this out, x squared minus x plus 1/4 plus y squared equals 1/4. And so we could subtract 1/4 from both sides. And move the x to the other side. Looks like answer A. Okay. All right. Number 2, if the function r equals f theta is continuous, non-negative, so it's always positive radius, from 0 to 2 pi, then the area enclosed in the polar curve and the lines alpha and beta is given by what? So, just generically, you got a curve trying to find the area from alpha to beta, and it's 0 to 2 pi, and it's always positive. So you'd use that area formula, 1/2 r squared d theta. And so we'd go 1/2 alpha to beta, and then it'd be f theta squared d theta. So this one has a squared in the wrong spot. This one doesn't have the squared. This one looks weird. This one looks weird. This one has a squared and it has one out front, so it's got to be E. All right, number 3, which of the following gives the area of the region enclosed by the graph? Okay, so we're just setting it up. I don't know if it could help because they might be making use of symmetry and things like that. So this is a cardioid, and we could set up a quick graph. So it's going to be 2, 1, 0, 1, 2. It's going to be facing the right. So 0, 2, 1, 0, 1. So that's what the graph looks like. So if we're trying to find the whole area, we could take advantage of symmetry. You'll notice most of these don't have the 1/2 front, so probably going to do symmetry. So we would do A equals, I'm going to double the area from probably 0 to pi. It could be pi to 2 pi, right? So, it could be pi to 2 pi. Right? Pi to 2 pi will give you the same thing. So 0 to pi, this squared's in the wrong spot. This one looks That one looks good. This one doesn't have the squared and the limits are wrong. This one, the limits are wrong, but it has a squared. And this one is the whole thing. That could work, but the squared would be need to be right there. Okay. What's the area of the region enclosed by the polar curve? Okay, that looks like a weird curve. And we could try and sketch it. I mean, one of the things I think we just need to verify is that the pattern will take 2 pi to finish. And then other than that, we should be able to, just calculate it. But that's going to be 2. That's going to be 2. That's going to be -2. That's going to be -2. That's going to be back to 2. And so we could try and graph this. So 0, 2, pi over 2, 2. Pi is over here, but it ends up back on there. 3 pi over 2 is down here, but it ends up back over here because it's probably some kind of circular shape or something, but it is repeating in 2 pi. So that tells us that we should probably do just 0 to pi to get the whole area. So that would be our setup. Now we're going to see if we can figure this out. So 2 gets squared, and you put it out in front times 1/2, you end up with just a 2. And here we're going to get sine squared theta plus sine 2 sine cosine, and then plus cosine squared theta. Okay. So we're going to have to use those double angle identities. Well, no, actually, sine squared plus cosine squared is 1. Right? That just gives you a 1. So we can avoid all that double angle stuff. This, I think, we'd use U substitution on. So we're going to factor the 1 by itself. And then we're going to do the U substitution. Now, the U substitution, there's another 2. If I do U equals sine or cosine, I think sine would probably be easier. Less negatives. So that would be U du, right? So the antiderivative of that's going to be theta. This is going to give you 4u squared over 2, which is going to be 2 sine squared. And so we're going to get 2 pi from that. This one, we could show more work, I guess. This one, you plug pi in, you get 0. Plug 0 in, you get 0. So final answer is just 2 pi. Okay, worked out. Okay, number 5. The area enclosed by the polar curve from 0 to pi. I mean, I don't think we need a sketch. They're telling us specifically what to use. So I think we're going to do 0 to pi, and then it's going to be 6 cosine theta plus 8 sine theta squared. And I guess we're just trying to work it out. So it's going to be 36 cosine squared theta plus 48, 96 sine theta cosine theta plus 64 sine squared theta. It's kind of crazy. Okay. I think we're going to need to use those double angle identities. So this would be 1/2 plus 1/2 cosine double angle. And this one's going to be 1/2 minus 1/2 cosine double angle. So we're going to get, see if we can start grouping some of these terms together. So we got 18, 18 plus 32 is 50. And then 18 cosine squared minus 32 cosine squared is going to be minus, so 18 minus 32 is going to be minus 14 cosine double angle plus 96 sine theta cosine theta. Now we're going to use substitution on this one. So this is very similar to the last one. We're going to do u equals sine theta, du equals cosine theta, d theta. So this would give you 96 u du. And so then you would get u squared. You would get u squared over 2. Okay, so let's see. We got a 50 theta minus 7 sine 2 theta plus 48 sine squared theta. So that's the antiderivative. So 50 pi minus 7 times sine of 2 pi is 0, plus 48 sine of pi is 0. 0 minus 7 times sine of 0 is 0, plus 48 times sine of 0 is 0, squared is 0. So lots of terms drop out, and the final answer looks like it's going to be 25 pi. All right, okay. Which of the following integrals gives the total area of the region inside both polar curves? These are both circles. I think we should draw a quick sketch. 0 pi over 2 pi. This is going to be 2, 0, 2. And then the other one is going to be 0, 2, 0. So if we graph these together, okay, so the first one, the cosine one, is here. You need to keep track of which one's which. So that's that circle. So that's the r equals 2 cosine theta. And then the other one is here. That's the sine one. Okay, so we're trying to find the area that is inside both of them. So that would be this area. And so we need the intersection, which I bet is pi before, but we'll verify it. And then we could find this area, and then we find that area and add them. Or we can find one area and double them because it looks symmetric. So they look congruent. Let's just confirm the intersection angle. So when does cosine equal sine? Well, pi over 4, quadrants 1 and 3. So pi over 4 and 5 pi over 4. So that one's pi over 4. It's the first quadrant. All right, so if we're saying the area, what we could, now we're at their mercy, but one idea is, one thing you could do, you could say 1/2 0 to pi over 4, and that would be of that circle right there, 2 sine theta squared. And then you could do the other one from pi over 4 to pi over 2, and that would be the cosine one. So this is maybe the most obvious setup. Now, what we could do is probably take advantage of one. So if you look at a lot of these, if a lot of them are just 0 to pi over 4, 0 to pi over 4. So it's probably going to do this one and just double it. And so the 2's cancel, but there is a 4 that gets brought out front. So it's probably going to be this or something like this. 4 is over pi. There you go. All right. Okay, this one's interesting. The graph of this has 3 petals. The graph of this has 5 petals. Which of the following statements about R3 and R5 are true? The area enclosed by 1 petal of R3 is larger than the area enclosed by 1 petal of R5. The total area enclosed by 3 petals is less than the total area enclosed by the 5 petals. The total area enclosed by the 3 petals is greater than the total. I feel like we're talking about area, so we should probably go and find the full area of each of them. So if we find the full area of each of them, be 1/2 0 to pi, because they're odd number petals, sine 3 theta squared. So let's see if we can figure this out real quick. We would have to use doubling the identity, so it'd be 1/2 minus 1/2 cosine 6 theta, right? And then so then the antiderivative would be 1/2 theta minus 1/12 sine 6 theta. And then we plug pi in, we get pi over 2 minus 1/12. The sine of 6 pi is 0. Plug 0 in. 1/12. The sine of 0 is 0. So those all go away. So we get pi over 4. That's the total area of the 3-petaled, okay, which means that each petal would be 1/3 of that, okay? Now let's do the other one real quick. 1/2 0 to pi of sine 5 theta squared. So a lot of similar work. 1/2 minus 1/2 cosine 10 theta. 1/2 theta minus 1/20 sine 10 theta. Plug pi and get pi over 2 minus 1/20. Sine of 10 pi is 0. Plug 0 in. Sine of 0 is 0. And we get pi over 4. That's crazy. They have the same area. That's for the 5-petaled. They have the same area. So each petal in this one, though, is going to be pi over 20. So here's the crazy thing, is that flowers with the same radius, but different numbers of petals, have the same area in them. The total area is the same, but then they just get, obviously if there's more petals to divide the same area, then the more petals there are, the smaller each petal is. So the area enclosed in 1 petal for R3 is larger. Yes. The total area enclosed in 3 petals is less. No. They are equal. The total area enclosed by 3 petals is greater. No. They are equal. So it's going to be 1 only. But that's kind of interesting thing that we never really talked about. Okay. What is the slope of the tangent line? I feel like it's been a while since we talked about these things. This is good. We're going to have to start reviewing for the whole, everything. Slope of the tangent line to this curve. So this is where we use x equals r cosine theta. And we use y equals r sine theta. And we want to find dy dx, which is going to be dy d theta over dx d theta. So dy d theta is going to be 2 theta cosine theta plus 2 sine theta, product rule. Dx d theta is going to be 2 theta sine theta negative plus 2 cosine theta. And then we're going to plug theta equals pi over 2 into this. And so we're going to get pi over 2. Cosine pi over 2 is 0. Sine pi over 2 is 1. So we get 2 over negative pi. There you go. That's how we find slope. Polar curves, dy dx, dy d theta over dx d theta. Let's see, 9, the expression representing the area inside one leaf of a polar rose is given by what? Well, how do they want us to do this? Can we do the whole? There's two strategies. Say this has 4 petals, so we could find the area of all of them and divide by 4. The problem is I don't think any of these really look like that, because that would be 1/4 of 1/2 of 0 to 2 pi 3 cosine 2 theta squared d theta. That's what that would look like. And I don't see any answers that look like that. So I think we're going to have to get a little more into like where are the petals at. So I think a sketch would be helpful here. So there's 4 petals. We want to find the tips of the petals by setting the radius equal to the extreme radius. So 2 theta equals 0 plus pi k. Theta equals 0 plus pi over 2k. Theta equals 0, pi over 2, pi, 3 pi over 2, 2 pi. So that's where the tips are. I'm going to do a quick sketch. The radius is 3. So the first petal is here. The next one's here. Next one's here. Next one's here. Draw these angles that cut those angles in half. So that's the first petal. That's the second petal. That's the third petal. That's the fourth petal. So the first petal, what we could do, this is theta equals pi over 4. This is theta equals 0. So a lot of these have 0 to pi over 4, 0 to pi over 2. 0 to pi over 4 would give you half a petal. So that seems promising. We could do double a half a petal. 0 to pi over 4, 3 cosine 2 theta squared d theta. So we could do that. So then we'd have 9, 0 to pi over 4. And I guess we're not going to actually find the answer, so we don't need to use the double angle identity unless their answers are like that. But I think that looks like, is it this one? Looks good. This one still has a half, so this is only half of a petal. This one's going this half, and then you would end up getting this half over here, which I don't know if those would add up. I mean, it seems like that could work, though. It could work, but then it would need a 1/2 in front. So that could work, but it would need a 1/2. And these ones, I don't know what those are. Those look like arc length or something. Okay. The area of the region inside the polar curve and outside the polar curve. So that you have 2 curves. I think we should draw a quick sketch. This is a circle, and this is also a circle that is a really simple circle that we don't really see that often on polar. So it's going to be 0, 4, 0. So the sketch, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so That one is going to be 0, 0, 0, 4. It's going to have a radius of 2, diameter 4. So that's that one. And this other one is just like a really simple circle with a constant radius of 2 centered at the origin for all angles. Okay, so we want the area inside this curve, but outside the other one. So that's this area right here. Okay, and we're definitely going to need to find this angle, or this angle right here, because that's where we're going to stop and start it. So we would get that by setting these equal to each other, which is pretty easy. Pi over 6, quadrants 1 and 2, which makes sense with the picture. So pi over 6 and 5 pi over 6. So this is pi over 6, and this is 5 pi over 6. Okay, now our strategy is probably to find the area inside that circle and then subtract the area inside that circle. And then we could double it, maybe. I mean, so we could do 1/2, and we could do pi over 6 all the way to 5 pi over 6. We don't have to do symmetry. And then the top curve is the 4 sine theta. And then the other one, we do the same thing, but we subtract it. So, I mean, that's kind of like a straightforward setup of that. I don't know if we see one in here that's like that. Now, they do have the same. I see a lot of these have pi over 6 to 5 pi over 6. So maybe the pi over 4 ones don't even make sense. And I don't even feel like these make sense. So we could combine them into a single integral based off of what the answers look like. And that would be 16 sine squared theta minus 4. And they both have 1/2. I think that looks like that one. You got to score them separately, though. So this one doesn't make sense because of that. Okay. And we got one free response problem. Now, the last free response problem we did on the previous assignment was really not very polar. It was more rectangular with a little polar. But this one looks promising, like a little more like what you're probably going to see usually for response problems with polar. So let's see. And they give you a graph, like I said before. So it's probably like a limacon with an inner loop, and they're just giving you like half of it, you know? Okay. 0 to pi, so just half of it. Let S be the region and the quadrant bounded by the curve. So that's S right there. Write an integral expression for the area. So just write the expression. You don't have to find it, just write it to find the area inside of S. So we got to figure out, well, where this, you might actually, okay, I'm thinking maybe theta equals 0. That gives you -1, right? If you're doing, and that's where it starts. And then I think it's going this way. We got to figure out when it hits the pole. Okay, so I think we're going to solve for that. Set the equation r equal to 0. And that's going to be positive 1/2. So this is going to be pi over 3, quadrant 1, quadrant 4. So pi over 3, 5 pi over 3. But clearly we want the first one. So that is theta equals pi over 3. Now you probably want to show this work here. You can write stuff on your picture, that's fine. That's just for you. That's not giving you points, but write work here. Okay, so this is where it ends, right? And it begins at 0. Okay, so we want the area. It's going to be 1/2, 0 to pi over 3. of the radius squared. And I think that's probably good enough. That's it. Okay. All right. B, write expressions for dx d theta and dy d theta. Okay, well, x equals r cosine theta. So 1 minus 2 cosine theta, cosine theta. And so dx d theta would equal 1 minus 2 cosine theta times derivative cosine is sine theta with a negative, might make more sense, but there, plus cosine theta times 2 sine theta positive. I think that should be fine for dx d theta. And then y equals r sine theta. Writing this stuff down could actually get you points because that's crucial and it involves your knowledge of polar. So if you at least know that you're supposed to do that, then it can help get you some points. No, I don't think we need to simplify these. This is it. There you go. And C says write an equation in terms of x and y for the line tangent to the polar curve at the point where theta equals pi over 2 show the computation to lose your answer. Now on the picture, I'm trying to find the equation of tangent line at theta equals pi over 2, which I'm trying to find the equation of that tangent line right there, which might be good just for your own self to sketch it. Better have negative slope. Better have y, x equals y intercept. So we need a tangent line at theta equals pi over 2. So you need two things. You need the point, which I think we could, I don't know if we could just pull it off the graph, but you can plug pi over 2 into this expression right here. Cosine of pi over 2 is 0. Cosine pi over 2 is 0. So you get 0 for the x, which is not surprising based off the graph. And plug pi over 2 into the expression for y. So it'd be 1 minus 2 times cosine of pi over 2 is 0. Sine of pi over 2 is 1. So you get 1. So, I mean, that's what it looked like. Looked like it was 0, 1. So you need a point. You need a slope, dy dx, which comes from dy d theta over dx d theta, which we just found in the last problem. So we could just use those. 1 minus, and then we're going to plug theta equals pi over 2 in. So we're going to plug pi over 2 in. Cosine of pi over 2 is 0. Cosine pi over 2 is 0. Sine pi over 2 is 1. Sine pi over 2 is 1. And then the bottom is going to be negative 1 minus 2 times cosine pi over 2 is 0. Sine pi over 2 is 1. Cosine pi over 2 is 0. Sine pi over 2 is 1. So that term goes away. That term goes away. We're left with positive 2 over negative 1. So we get negative 2 slope, which again makes sense from our picture. So the equation of the line is going to be y minus 1 equals negative 2 times x minus 0. You could write it like that. You could write it in slope intercept form if you want. Whatever. So there you go. That's it.